with the Fourier transform. So we were here yesterday, so we defined what a two-dimensional sinusoid is. So it is a signal, it's a wave that looks like a sine in one direction. So in the propagation direction, it looks like a sine, and then it has the properties of a sine. So it has an amplitude, it has a period, that is the distance in the space between two equivalent points, and then it has a phase that moves the wave back and forth along the direction, the propagation direction. And in general, we can write it in this way. So it doesn't matter if it is divided by 2 or no, or so on. But yeah, the interesting part is that it has an amplitude in front, and then you have frequency. You can write the frequency in the standard way with omega or 2 pi for lambda, and lambda is the wavelength. And now, because you are in 2 dimensions, you have a propagation direction. So you have to define in which direction you are propagating, and that is given by theta. And then the phase. And to explore a bit more about this idea, this we saw already yesterday. So that when you have a Fourier, you have an image, you compute the Fourier transform, and then Fourier transform. This is the frequency space. The frequency space will have an origin. We will talk more about this today. And then, so here we have a joke. Alexandra, you too.
What's up, steps? Unfortunately, the steps don't talk.
Alexandra.
The patient is going to the doctor, and the doctor asks, "Hey, how are you?" Patient says, "Thank you, I'm fine." All right then, get out.
Okay, so in this Fourier space, the low frequency components are close to the origin, and the high frequency components are closer to the edges. And again, we will see this in more detail today. And we already expressed the frequency in polar coordinates, and then we also calculated, or we reasoned that there are a few wavelengths and frequencies associated. And I think this slide, shows very nicely this idea. So you have a frequency or a wavelength in x, so that is the distance between equivalent points in x. So these points here, they are equivalent. And then you have another wavelength in y. So in y, the distance between the equivalent points is much longer than the distance in x. So there are 2 wavelengths. And then you have another wavelength, that is the wavelength in the direction direction of propagation. So along this line, you have a different distance. And then you can relate the 3 distances this way. So you can compute the wavelength in x, the wavelength in y, and then the wavelength in the direction of propagation. It uses what is the size of the image and what are the 2 frequencies that you are looking at. Okay, so then once you have wavelengths, immediately you can have frequencies. It is simply the inverse. So you inverse the wavelength in x, and you have the frequency in x. You take the inverse of the wavelength in y, and you have the frequency in y, and the same for the in the direction of propagation. And then the direction of propagation, this angle, can be calculated as a function of these 2 frequencies. This is just a reorganization of the calculation. So is the same. Okay, so yeah, the same idea again. So given the, yeah, this is the same. Okay, so now the Fourier transform is a complex number, so we can represent the real and imaginary part as we did before. But as it is a complex number, you can also put it in polar coordinates. So you should not confuse these polar coordinates, that are the polar coordinates of the Fourier transform, from the polar coordinates of the frequencies. So those are two things. So let us represent it. So let's say that we have here, we have Wx, Wy, is 2, 3, that's it. And here we have the Fourier transform. So it is the limit Fourier transform at that location. Okay, so now we have in this plane, we have, let's say that we have a particular frequency. So we have this frequency here. So in this plane, it is where we have omega theta. And at that location, you have a Fourier transform. So this is the value of I at that location. And that is the one that, let me see the letters we have been using. A and phi. Okay, this is the one that can be written as A, J, phi. Okay, so you have two polar representations. The first polar representation is for the frequencies here. The second polar representation is for the Fourier transform there. Okay, good. So, although that is the polar representation of the Fourier transform, not the polar representation of the frequency. Okay, good. Then, here we have all the ingredients of this Fourier transform. So the frequency defines the wave, but the Fourier transform, so this part, A and phi, define how wide the wave is and how it is shifted. Okay, so the frequency determines the orientation of the wave, while A and phi determines the height and the shift of this wave. And then we can, instead of representing the real and imaginary parts, we can represent the amplitude and the phase of that. So this would be A, this would be phi. And it is difficult, typically for any signal images too, the low frequency components, they have orders of magnitude more energy than the rest of the Fourier transform. So that is why you take the logarithm. So instead of representing just the amplitude, you represent the logarithm of the amplitude. So that if you have different orders of magnitude, they are more comparable to each other. And we will learn to, we saw it yesterday with the house and the wall of the house, the roof of the house, and so on. But there are features of the image that are already seen in the Fourier transform. So for instance, this image, somehow in this direction, it has a lot of information. We have a lot of orders along this direction. While in this direction, it is very smooth. So that is seen here. So in this direction, you need a lot of energy in this direction, of waves propagating over there. But in this direction, it is almost zero everywhere, and then a delta, and then zero again. And let us think of that. Okay, so what is the Fourier transform? So let's say that we have a signal here, x of t, that is a constant, any constant k. What is the Fourier transform of that? The Fourier transform of that signal, which one is it? The delta. This is k delta omega. No? And that is what we are having there. We are having a kind of delta. So it is not truly constant. That is very smooth. So if you take any line, for instance, this line is almost constant. You see? And in general, okay, it is not exactly constant, but there are very little variations. And you have almost a delta. So you have almost zero, and a delta, and then zero again. Okay, then, and we may represent real and imaginary parts. Here comes an interesting idea. I will use okay, so we said it yesterday. You have a signal x of t, that is whatever it is. And let's say it is a sound. Okay, so let's interpret this as a sound. Let's interpret this as an image. An image in the sense, okay, this is a line of an image. Okay, so what do we see, or what do we hear? So if you do the Fourier transform of things, we are mostly sensitive to the amplitude. So what we hear is the amplitude of the Fourier transform, mostly. And what about images? What we see is the phase, mostly. And there is an interesting way to show that. Okay, so and it is the following. This is what I have, some other slide. Okay, so that's presented here. Okay, so let's say that we have two images. We have the image of a duck and the image of a cat. And then I take the Fourier transform. So those are the two Fourier transforms. Somehow there, we are representing the complex numbers. The intensity is represented how far you are from y. And then the color is the phase. So we are representing the complex numbers there in the same plot, but by using this trick. And now you know these tricks. You know already the HSV color code and so on. So you can play. You put one information in one channel, the other information in the other channel, and then you have color images. Okay, so now you take the amplitudes from this image and the phases from that image. Okay, so the amplitudes are coming from the duck and the phases are coming from the cat. But now you have a new Fourier transform. Now you do the inverse Fourier transform. What you get is a cat. It is not a perfect cat, so there's some ringing around, but it is a cat mostly. So that means that most of the visual information is coming from here. It is coming from the phases. And it makes sense because the phase is controlling where the wave is starting or where the peaks of the waves are in space. And then if we think we only see edges, so if I look at this table, the important information of the table is where the edge is. And where the edge is where the peak of this wave is. So we are sensitive to the location of the peaks rather than the amplitudes of those peaks. most of the visual information is in the phase, it is not in the amplitude. Okay, good. Then, yeah, we have a real imaginary part. This is a bit of, okay, so what is the amplitude? So the amplitude, you have to fully transform. And there are many things you know. Okay, so you have, let's put it here. So you have an image, you have the Fourier transform at a particular point, and then you want to compute A. So you want to compute A. A very simple way is to compute A squared, that is I at that location, multiplied by A complex conjugate at that location. And there. Yeah, this is simply if I, let me put it in this way. So if I is equal to A plus JB, say that is a complex number, a generic complex number, then this is A squared plus B squared. Okay. And just to be complete, how do you compute phi? So that's phi there. Phi is there. Tangent is B divided by A. But these things, you know. Okay, so then, yeah, and this is a reminder again of the same ideas of before. So the lambda is 1 over this square root. So this is the length of the frequency vector, and this is the arc, the same arc tangent, but now in the frequency space. Okay, and this is MATLAB. Power spectrum. Power. So let's say that we have calculated a Fourier transform. You may remember the expression power spectrum density. So in one dimension, it looks like this. So we have here power spectrum density, and the power spectrum density depends on omega. Let's say it is something like this. And then, if you integrate in some region, you have to take the two regions that are equivalent. Though that area is the power within that range of frequencies. So power in this delta omega, and this is the delta omega that you are analyzing. So it gives you how much energy you have. It is called density. What do you
call a Mexican with a car? Mexican.
So if you integrate over frequency, then you have the power in that region. So you can calculate how much energy do I need from this kind of waves. So this area, this region in frequency, tells you which kind of oscillations you need, how fast they are, and then by calculating this area, you are calculating how much energy do I need from this kind of size to reproduce this signal, and then you can design filters and so on. Okay, so power spectrum density. The concept is that. How to calculate this? Okay, so there are a few ways. So the power spectrum density is always calculated on something. So it is the power spectrum density of the signal X. and it is a Fourier transform of the autocorrelation of X. Let me do it in 1D, because I think in 1D it is more visible. So this is the autocorrelation. How do you define the autocorrelation? The autocorrelation in particular, this is called a lag. This is the expected value of x of n, x of n plus n. Okay, so what does it mean? Okay, so if you have a signal, let's say that you have this signal, yeah, this whole thing. You have this signal here, x of n, here n, and you have some samples, that kind of random. They don't need to be random, okay, but they also apply to random signals. Then, given a particular n, so given an n, any one, I have chosen n equals 0 for simplicity, but you can take any one. Then, how much you can say if you add m? Okay, so what is the information that this sample has on this one? And then here n is equal to 3. Okay, so you take equals 4. So you take one sample. How much can you say of a sample that is 4 samples later? And the same for any pair of samples. Okay, so this would be also a valid pair. This one and this one. How much can you say of this? Actually, the expected value is taken by making these calculations there. So taking all these samples, all these pairs into account. Okay, so this is the generic definition. And then if your image or your signal is deterministic, then this is the Fourier transform of the square. Yeah.
What is this E?
What is this?
E.
Is this one?
Yes.
This is the expectation operator. Do you know when you calculate the mean of something, you have taken the expectation of that random variable. Okay? And the difference between deterministic signals and random signals, you know it, right? So deterministic is a signal that it is all the time the same. When we look at the picture, it is a deterministic. It is every pixel has a particular value, and it is what it is. So for images without noise, this power spectrum density now in 2 dimensions. So we go here. A little bit more. So this power spectrum density, this is equal to the power spectrum density of the image I at the frequency omega. But this is only for deterministic signals. If it is a random signal, then you have to take the Fourier transform of the autocorrelation function. And how to extend this to multiple dimensions. So how do we calculate the autocorrelation of an image? Okay, so let's extend it. So let's do it in a different color. So for images, now the lag is a vector. So we will have 2 lags, one in x, one in y. And then we have to do the same. It is the expected value of the image at a particular location. Lag times I at that location, that's the lag. And the concept is the same. So given a pixel, how much can you say of a pixel that is separated by the lag? If you cannot say anything because it is completely random noise, then this autocorrelation will be 0. Okay, good. So here what we have is just this expression of the power spectrum density that he does not justify, but he introduces it as the Fourier, the module squared of the Fourier transform of the equation. Okay, good. There is a little mistake here. Can you spot a little mistake? In that expression, there is a mistake. U and V are frequencies. So you cannot do, so this is the Fourier transform already, so you cannot do an image that is in Fourier space and then do the Fourier transform. You cannot do that because it is already in Fourier space. You can take the inverse Fourier transform if you want. So this should have been the spatial coordinates, not the frequency coordinates. Okay, good. Then, yeah. Then there is something that is interesting, and probably you have not thought too much about this idea, but you already know. Okay, so let's give a couple of examples. Actually, we used already one. Okay, so let's say that x of t, let's do it in 1D all the time because it is much simpler. Okay, so let's say you have a signal that is a constant. What is the Fourier transform? Say this is a delta. So this is the omega and coordinate, and let's represent the modulo. Okay, so if I have a signal that is extends from minus infinity to infinity, the Fourier transform is a delta. What about this one? So this one, this is a sine. This is sine. And again, the Fourier transform is a couple of deltas. What about the following? Now we have one that is a delta. So this is x of t all the time. This is t. This is the Fourier transform of a delta. This is a constant. Okay, the module is a constant. So we start to see the pattern. So if my signal extends from minus infinity to infinity, these two cases, the Fourier transform is very compactly supported. So it is supported. So which are the points, which is the size of the set of frequencies whose Fourier transform is different from 0. It is just 1 point, 2 points. On the other side, if my real space is just 1 point, the support, this is called the support. So the support of my signal. So the support of the signal is the arguments of this t such that x of t is different from 0. So the support is just a point, then in the Fourier space it is infinitely supported. So there seems to be a kind of trade-off between the two. So if this is wide here, then here it is very short. If it is short in time, it is very wide in frequency. And that is a pattern. So you may define somehow, this is a very loose definition, but we don't have even a definition on the slide. But you may try to measure more or less what is the extent of this signal. So let's somehow encode this by delta t, and delta t is more or less how much space you need to define your signal. So here delta t is very wide, here it is very wide, it is infinite, and here it is very small, and here we would have delta omega. And again, here it is very compactly supported, here it is very compactly supported, here it is very wide. So it turns out that the product delta omega delta t has to be larger than something. Okay. And we don't care about what this something is precisely, but we care about the idea. So if you are very wide in frequency, you are very compactly supported in real space, and the opposite. If you are very compactly supported in real space, then you must be very wide in frequency. And that is called the uncertainty principle. Have you heard of the Heisenberg's uncertainty principle? Yeah, that you cannot specify infinitely precisely the location and speed of a particle. Actually, it is the formal mathematics of all that are much more complicated. But somehow they are related to this. So you cannot locate a particle in time and in frequency at the same time. Frequency and speed are very much related. And it is the same for signals. So you cannot define, you cannot determine the location of a signal or an image in real space and in frequency space at the same time, infinitely precisely. Yeah, so here it is, they give a constant there. These things should be taken with care. Depends on what is your definition of. Yeah, actually, in the real Heisenberg's formulation, there is no delta x, delta y, there is a sigma. We don't care. So, but the idea is correct. The idea is if your image is compactly supported in real space, it must be wide in frequency. And if it is wide in real space, then it is very compactly supported in Fourier space. Okay, then let's look at some examples. Okay, so let's say that I have a couple of points in my frequency space. What do I get? I just get a sign, and it behaves the same as in one dimension. So the Fourier transform of a sign is a couple of deltas. Here I have the couple of deltas. And the theta is equal to 0. So they propagate in that direction. This is where the sign is propagating. Okay, so now let's say that instead of a couple of deltas, I have in this direction a couple of deltas, but in this direction I have constant. So now my new Fourier transform will be this. Okay, so it is 1, 1, 1 everywhere, and then 0 in this direction, except for 1, then 0, 1, and then 0 again. Okay, so now, what is the inverse Fourier transform? Okay, so in this direction, what I see is a sign. Okay, so what I see in this direction is just a couple of points, so it should be a sign. What I see in this direction is a constant. So if it is constant in frequency space, in real space it is a delta. So what I have is the multiplication of this sign with the delta function. And then everything goes to 0 except this line. And what about this one? Okay, so let's say that I have this image This is the Fourier transform. So here we are separating amplitude and phase. Okay, what about the amplitude? Okay, so in this direction, they look like constant. You see? So it must be a delta. In this direction, they look like a step function. And the step function, the Fourier transform of a step function is a sink. Okay, so here I have the sink. Only that it is a sink that I don't see the oscillations, but and what about the phase? So if you look at the phase, this signal, yeah, you may remember this, what are they called? Linear phase signals. Have you studied that? Signals with linear phase?
Systems.
And systems of linear phase. Yeah. So a system of linear phase is a system whose impulse response is symmetric. Okay. So let's see. So it has some kind of symmetry, and there are two kinds of symmetry. So let's say that we have an impulse response of h of t. There are two kinds of symmetry. One is this one. So let's say that this is our impulse response. And this is even symmetric. And the property of this is time. The property of this even symmetry is that h of t is equal to h of minus t. So there is a kind of mirror around this axis. And we have another kind of signals that are odd symmetric. So we have h of t, and they are odd symmetric. And we have h of t properties that they are negated. Okay, so they look something like this. So let's say something like this. So now the symmetry is around this point. Yeah, also something interesting. If you have a low pass filter, which of the two can be a low pass filter? Which one? The even symmetric. And why? So this is a low pass filter. And these ones are high pass filters or band pass filters. They have to. Why?
Because the transform of the scene is a rectangular course.
Is it?
A rectangular course.
But yeah, I have drawn here kind of thing, but I could have drawn also this one. I could have drawn this one. Maybe it's also a low pass filter, and you don't know the Fourier transform of that. But why is it a low pass filter? Let's think of the properties of convolution and Fourier space. Okay, so we have x of t convolved with h of t. This is my output. Okay. Now I do the Fourier transform. So I do the Fourier transform. Sorry, this is y. Okay, omega is equal to x omega. Okay, omega times h. Okay, now this is true for all omegas. What about this one? Omega equals 0. For omega equals 0, this holds true. A0 is equal to A0, H, A0. And what is omega equals 0? It is the DC component. It is the constant. It is the one that is absolutely, so the average of our signal. Okay, so let's study h of j omega 0. Okay, so h of j omega 0. Any signal, but let's make it clear. It is the integral of h of t minus the frequency at the frequency 0 times t, differential of t. So this is 1. So this is the other. This is just the area under the curve. So, and what is the area under the curve for this kind of signals? 0. All this area here, the addition of the whole area is 0. While for these ones, the addition is not 0. So low-pass filters have to be even symmetric, or not they have, but even symmetric filters, they are low-pass filters. And this one, they have to be low-pass or high-pass or band-pass filter. You see? Okay, good. Then we were here. Linear phases. Okay, so there is a property of this kind of signals. If they are symmetric, so only for symmetric ones, the phase of the Fourier transform is a line. Okay, so the phase of the Fourier transform is a line. Okay. And the same for this one. The phase is a line. Actually, I think for symmetric it is 0, but I'm not sure. I don't want to state that. It is a line. I think for even symmetric it must be 0, but I'm not sure about it. But that means that linear phases, they should imply some kind of symmetry. Is this signal symmetric? Has this kind of odd symmetry, right? So around the point, you have something that is on one side or the other side. So it is kind of the odd symmetry that we define for. And that is why you get this linear phase. Okay, good. Then a bit more examples, a few more examples. So next one will be a bar. And now we start understanding how these things behave. So in this direction, it is almost constant, so it should be a delta. In this direction, what I see is a pulse. In this direction, what I should see is this kind of signal. And again, there is a kind of symmetry. So there is now an even symmetry. So that was right. In general, they are linear, not 0 phase. So in general, because of this even symmetry, what we have is a line in this phase. And now, yeah, this is complicated to explain it that way. I think it is more clear to explain this way. Okay, so we said you have a signal. Let me do it in one dimension first. So you have a signal, x of n. Now you have n here. And this can be whatever. and then zero. So it doesn't need to be periodic or whatever. So you do the Fourier transform. Fourier transform is correct. So you do the Fourier transform, and now you have something that is like this. And remind always to label your axis. I made a mistake here. So this is not 5. 5 should be a little bit farther. Okay, so this is my Fourier transform. Then, because this signal is discrete, this one has to be symmetric. Symmetric periodic. So at 2 pi, it is repeated. And at 4 pi and 6 pi, and on the other side at minus 2 pi, minus 4 pi, and so on. So it has to be periodic. Then I can tell you, normally we like to think of the Fourier transform in this region. But if I tell you the Fourier transform in this other region, I'm giving you exactly the same information, only that omega here, it goes from minus pi to pi, and here omega goes from 0 to 2 pi. But the appearance of the Fourier transform would be very different. So if I use a numerical library to compute this Fourier transform, in the first case, so both, and I use 2 implementations. One will give this one, the other one will give the green one. Okay, so the appearance of the first Fourier transform will look like this. So it will be a vector, then it will be almost 0, then something, and then 0 again. But in the other implementation, the appearance is different. So it will be vector, but then at the beginning it is different from 0, then a lot of zeros, and then different from 0 again. You see? So most FFT libraries, FFT, you know, fast Fourier transform. So most FFT libraries work like this. They don't like to work in this way because the way it is fastest to calculate is by using omega that goes from 0 to 2 pi, not one that goes from minus pi to pi. So all the libraries goes like this, or most of them. Okay, but as humans, we find it more difficult to see in this way. We prefer this one. So there should be a way of translating this one into this one. And this is called the FFT shift. Okay, so now let's do it now in 2 dimensions. So now in 2 dimensions, I have an image. So this is my image in real space. Now I do the Fourier transform. And we like to think of it in this way, in which we have minus pi, minus pi, and then omega y, omega x, and there will be some kind of Fourier transform there that is high at low frequency and low at high frequency. So they will be like this one. So this one has more energy at low frequency and then lower energy at high frequency. So we have something that is like that. But this is periodic. So this is periodic, meaning that there are copies of this. There are a lot of copies, infinite copies. Let me erase this part. Okay, and there are infinite copies. Everyone said that this is the 0, frequency space, 0, frequency in this direction. That is, let's put first y, so this would be 2 pi 0. But 2 pi 0, I have another copy. And this is, let's say, this one here is 0 minus 2 pi. And I have another copy. And at this point, that is minus 2 pi minus 2 pi, I have another copy. And so on. But then, and here there are also copies. So let me put these two. I'm not writing the frequencies anymore. Okay, so now the Fourier transform, the FFT libraries, they like this copy. So what you see in the Fourier transform of an FFT library is something like this. We have energy there, energy there, energy there. Those corners, they are the low frequency corners. And the high frequency, so this part is low frequency. This part here in the middle is high frequency. So the way we like to think, the low frequencies in the middle and the high frequencies are in the borders, while the way the FFT calculates, the low frequency is in the corners and the high frequency is in the middle. And then there must be a way of going from this kind of representation to this one. This one. And again, this is the FFT shift. It's simply just shifting the square around. Let us now identify the regions. Okay, so let us repeat this part of the graph. But now I will be more careful about the labeling. Okay, so let's repeat it. So we have 4 copies. We have these. I will label that 1, 2, 3, 4. And then we have this copy, that is 1, 2, 3, 4. And then we have this copy, that is 1, 2, 3, 4. And then this copy, that is 1, 2, 3, 4. And now the FFT is calculating this. So that means that the FFT has 4 regions. The way they are organized is that this is 2, this is 3, this is 1, and this is 4. And there is also some interesting idea here. Because of the Hermitian symmetry, we know that the Fourier transform at a given location is equal to the complex conjugate of this. So that means if I take a point here, this is pi of omega, the Fourier transform at that point. And it should be the complex conjugate of this one here that is in front with respect to the origin. So this is what this means. So you take the point in front with respect to the origin, and now you take the complex conjugate. This is the origin. You take the point in front. So that means that a point here is symmetric with a point there. And the same for these two. So these two are complex conjugates, and these two are complex conjugates. And even a further refinement, if they are complex conjugates, if you give me one, you don't have to give me the other one. So most FFT libraries, they compute only a half of the Fourier transform. So they only compute this half. One. Because the other half can be computed automatically. So if I give you this half, the other half you can't. So when you do the Fourier transform in a computer library, you get this thing. Okay, so now let's think of something. Okay, so let's say that you have an input that has a size I. We saw it yesterday, so this is our English in real space. We saw it yesterday. What are the valid omegas? So the valid omegas, the k was a vector, and the kx could go from 0 to y minus 1, ky from 0 to c minus 1. Sorry. Yeah, reversed. C minus 1, R minus 1. Check the time. We are over time. Just tell me. And okay, so let me finish this argument and then we make the break at 30. Okay, so now, how many different frequencies we have? We have the same number. Oh, sorry. We have the same number of frequencies. So the Fourier transform has the same number of points. This Fourier transform here, it also has CR. But now we are keeping only half of it, and keeping only this half. So it will have together more or less R, C half. R, C half, complex numbers. Complex numbers. While these, they have R, C, real numbers. And now comes the interesting observation. How many real numbers do you need to represent a complex number? 2. You need A plus JB. So I need twice this many real numbers. So I will need twice RC divided by 2. Real numbers. So the size of this Fourier transform is the same as the size of the original image, even if you are keeping only half of it. But the reason is that you are keeping a half but complex numbers. So in total, the amount of memory that you need in the computer is the same. And now I promise, let's make the break 10 minutes. This is the FFT shift effect. So you start with something that is like this, and then you do FFT shift, and you will end up with this organization of the data, and the same here. Okay. And now the colors are mine 1, 2, 3, 4. Okay. So, but now we have labels with colors. Okay, then we do the Fourier transform of an image. We have this one. So this is FFT shift, FFT alone. So then you do FFT shift, and now the low frequency is enabled. Very good. Then same idea, but now we create it with labels, numbers, and so on. But it is the same. And this is a reminder of our setup. So we have, let's say, an index U and V that will be indexes in the Fourier space. So now this is the Kx, Kx, Ky in our notation. And we have put the origin in the middle. So this is also an interesting idea. So we mentioned here Kx, Ky, they go from 0 to c minus 1. This is true, but it is true. So let's have more space. It is true in this world where frequencies go from 0 to pi. So what goes from 0 to pi is omega x and omega y. If I go with kx, kx goes from 0 to c minus 1. And this is kx. And ky goes from 0 to y minus 1. So it depends on how you are counting. So if you are going in indexes, then you are going from 0 to 2. If you are going in indexes, you go from 0 to c minus 1. If you go in frequencies, you go from 0 to 5. Actually, we had yesterday this idea also that omega x k is kx times 2 pi divided by c. You remember? And here we have the same. Omega y is ky pi divided by r. And we call this part delta omega y. We call this part delta omega x. So you go from 0 to 2 pi in the steps of delta omega x, or from 0 to 2 pi in the steps of delta omega y. And how many steps? C steps and R steps. Okay, but then, so Kx goes from 0 to c minus 1 if you are in this world of Fourier transforms like this. If you are now in a world where your Fourier transform is taken in this way, now, and you put the origin there, now in this origin, let me do it separately. So in this new origin, Kx and Ky, they go, so frequencies again, frequencies go from minus pi to 5, minus pi to 5, minus pi to 5. This is omega x, omega y. The delta omega is still the same, so your steps have the same size. Here again. But now your k has to be negative. So k, here I'm kind of loose, okay? But k has to go from minus c half to c half, and from minus r half to r half. I'm kind of loose because there should be a minus 1 somewhere, so that there are exactly r and c columns and indexes. But loosely speaking, the length here is still c, and the length here is still r. But now the kx and ky can take negative values. So it is simply the way you index your frequencies. So if your frequencies, your step will be always the same. So if your frequencies are always positive, your k, your index will always be positive. If your frequencies can be positive and negative, now your indexes, they also have to be positive and negative. Okay. So where you place your origin in the frequency domain is very important. So we will see later that the origin here is placed there, and in this point it is placed there. So where is your origin? The 0, 0 frequency. Okay, so let's do that. So all this representation is assuming the origin is in the middle, or it is at the 0, 0. Okay. Now, so let's put the origin in the middle. Let's put the origin there. So now, and we will have omega x in this, omega y in this direction, omega x in that direction. So we can have different regions. You see, if you want to be exactly precise, it becomes a little bit clumsy. So that is why I said, okay, more or less it goes like minus c half, c half. If you want to be absolutely correct, you have to do this kind of things like c half and then round it down. This is also something that it is interesting for you to know. So when you have a number, okay, so let's say you have x equal 1.31, and you want to round it, you put like this. So x round is rounding to the closest integer. So the closest integer is 1. But you can always round down, and then it will be 1. But you can round up, and then it will be 2. So round down, is it round? Round is to the closest. Round down is to the closest integer that is smaller than that. And round up, that is the closest integer that is larger than that. So if you want to be precise, you have to take this round down c half and then c minus this thing minus 1. But loosely speaking, they go from minus c half to c half. And the same for r. Okay, so now, here it is the region with omega y, omega x. So these indexes here, they have positive values, both. This region here, they both have negative values. This region here, x is negative, but y is positive. And this region here, y is negative, x is positive. And yeah, so it depends on where your coefficients are. So in these coefficients here, this couple of red dots, they are defining a wave, as we know, and here too. And the slope of this, so the theta of this wave will be negative. The theta of this wave will be positive. Let us introduce that, explore that further. Okay, so let's say that we have, this is the origin, we have a single delta at this location. So a single delta will be sine. Okay, so it will be sine. Let's be more careful about this representation here. Let's use this one that goes from 0 to c minus 1. Okay. So let's use okay, I don't want to get it complicated, but yeah, let me explain it in this way. You have this signal. So like, and it goes +1 and -1 all the time. So it goes from -infinity to infinity, +1, -1. Okay, so you know what is the Fourier transform of that? So the Fourier transform of that will be a delta. So the Fourier transform will be a couple of deltas. So this is a sine. So if it is a sine, it has to be a couple of deltas. So it will be 1/2 delta omega minus y plus 1/2 delta omega plus y. Okay? So you need the two deltas. But this is the continuous way. But now you are taking samples. And you are taking samples every k and k. So we will have omega k, that is k, times delta omega. And this delta omega is 2 pi over number of samples that you have considered. And k goes from 0, 1 to n minus 1. And then there is something interesting. That is, in one of these samples, because of the minus 1, okay, because of the minus 1, one of these samples will reach -5, but the other one will be, so you will have omega k equals 0, omega k equals delta omega, then 2 delta omega, 2 delta omega, and all the way to n minus 1 delta omega. But n minus 1 delta omega is slightly smaller than 5. It is not exactly 5. This is slightly smaller. So you will take only, so one of the samples, one of these two deltas will be captured by these samples, but the other one will not. So that is why we don't have the equivalent point in this side. So this happens only for this -1, 1 side. And this happened, so this probably you knew from 1D signals. Okay, so now, okay, so a single delta can represent a sign, that is the final message. You don't always need 2. You need 2 for most of them, except for one, that is this -1, 1. And that has to do with the fast Fourier transform. Okay, so now that we have this sign here. So this sign here, the origin is there. So this is the maximally, the quickest sign that we can have. And this quickest sign has to go -1, 1 all the time. In which direction? In this direction. Because it is in this axis. So it will go in this direction. -1, 1. Okay. Now we put our delta in this pixel, to its space. So now it is a sign in this direction, -1, 1. Now we put it there. So if you put it there, what you have is the multiplication of the two. So you have this pattern. It's -1, 1 in both directions. Now, let's go for low frequencies. So at low frequencies, this is the smallest frequency that we can have. So, aside from 0. Okay, so now we should have a wave in this direction. And let's count the number of periods. So, how many periods are we seeing in this image? So we have a maximum, then we have a minimum, and then we are back to the maximum. So we see just one period. And this has index 1. So the index kx and ky tell you how many periods you will see in that direction. And in this direction, what is the kx and ky in this direction? So this ky, ky is 0. So you will see 0 periods in this direction. So kx and ky tell you how many periods you will see in each direction. So kx is equal 1, so you will see 1 period in one direction. Ky is equal 0, so you will see 0 periods in the other direction. The same here. Now 1 and 1 period. So we start at the maximum, then go to the minimum, then the maximum again. So we see 1 period. Then we start at the maximum, minimum, and maximum. So we see 1 period. And it propagates in this direction. Now this one. Now any arbitrary direction. So we take this 4, 3. So we will see 4 periods in one direction, 3 periods in the other. And what is the length of a period? The length of a period will be, for instance, we have to see 4 periods in this direction. So what is the length of that direction? We have C columns. We have 512, and we need to see 4 periods. So the wavelength is 512 divided by 4. And now we understand this formula that we had before. We have this formula that seemed to come out from the blue. It is not actually so. You have C columns, you need to see 4 periods. So those U and V are Kx, Ky in our notation. So they are indexes. And then the wavelength in that direction is C divided by U. C divided by Kx. You see? And in the other direction, the image is smaller in this direction, but the wavelength is the same, even if they have different indexes. Okay, more examples. So now we can calculate the wavelength associated to any direction, any axis. Same here. So there is no mystery. These are just more and more examples of the same idea. Yeah. So there is something interesting here in this one. That is, the wavelength is not exactly an integer number. So that means that this image, if you make it periodic by simply copying, the wave is not totally purely as it should. You see? So I have cropped my wave. The wavelength of my wave was not a multiple, or the size of my image was not a multiple of the wavelength. So I will be copying, there will be a little shift that is not making it perfect. Okay, so yeah, same idea all the time. So there is nothing really new in these slides. And I think it is interesting. Okay, this idea here. So the wavelength in one direction doesn't need to be the wavelength in. So for instance, let's consider this for 3. This for 3 index. You can compute what are the associated wavelengths in X and Y, but the wavelength in the direction of propagation, we have a different formula for that. And now it is much smaller. It is smaller. So from 128 to 80 something. So in this direction, we find the local, the minima and maxima much more frequently than in X and Y, and it makes sense. Okay, so let us maybe agree with this. So let me stop sharing here. me start sharing from the computer. Start sharing here. Can you see? And here we have the transform to the waves. So here we have what is the size of the image that we want to generate, and what is kx, ky. So we can say, okay, 0, 0. So 0, 0 should be a constant, and it is a constant. Okay, what about 1, 0? 1, 0 should be 1 period here, 0 periods in this direction. What about minus 1, 0? Minus 1, 0. Should be the same. They are symmetric. And what about 2? Now I see 2 periods. And you can play with this. And you can put, so what is the maximum number that I can put? 256. So you can be very low frequency in one direction and very high frequency or kind of middle frequency in the other direction. So when we do the Fourier transform of an image, what we are saying is that any image is composed, can be generated by adding this kind of signs. It's the same that we did yesterday with the square pattern, with this square pulses, and we were approximating the square pulses by adding the signs with the appropriate amplitude and phase shift. So if you shift these waves back and forth, and you compute the amplitude, and you add all those signs, you get any image in the world. And this is surprising, really, really surprising. Okay, what is the fastest? So let's put 0 here. So it would be 256. Now it is the fastest that we can have, and it is, let me make a zoom. So it goes minus 1, 1, minus 1, 1. So, any question up to here? No. You have this application, I saw it again. So you have the application, you can play your own by yourself. Okay, so let's stop sharing. Now let's start sharing from here again. Start sharing. Okay. Okay, so now we understand better these Fourier transforms that we will have. So any image, this is the Fourier transform. This is the amplitude of those coefficients. And now we understand what we are saying. Okay, so the amplitude is how much energy you need from each one of the waves. So here, in the space, we are representing absolutely all waves. So these are low frequency waves, these are high frequency in X but low frequency in Y. These are high frequency in X and Y, and so on. And they propagate in different directions. This one is propagating in this direction. This one's here, they propagate in this direction. And then here in the plane, we have absolutely all waves. And what I'm showing here is what is the energy of each one of those waves. So you will need a lot of energy from this kind of waves. You will not need so much energy from this kind of waves. So now looking at the Fourier transform, you can understand quite a lot of how images are constructed and what is the image content of an image or the energy content of an image. A couple of more examples. Yeah, and actually we already know this idea that I can decompose an image in amplitude and phase, But the interesting part of the image is in the information is in the face mostly. We did it with the duck and the cat. Just an example. This is the image type, then this is the amplitude, this is the phase. So this is another way to show this idea that most of the image content is in the phase. So let's say that you make the phase, you set the phase to 0, and you keep the amplitude, but you don't have any phase. Now, this is what you get. So this is not a very good representation of the original image. But now, let's do the following. You cannot set the amplitude to 0 because it would reconstruct 0, but set it to 1. So you set all the amplitudes to 1. There is no information in the amplitudes, but you keep the phase of those coefficients. You do a 3D reconstruction. This is what you get. It's not a good image either, but then now you can see at least the shape of what was there. So if you keep only the amplitude, you get nothing. If you keep the phases, you destroy the amplitudes, but you keep the phases, still you see something. Any question? No. Okay, so the Fourier transform is a tool that is very useful to deal with images, and probably one of the reasons is that they allow understanding the properties of many systems. So you may remember from linear systems that, let's say that you have a system, you have an input x of t, and you have a system A, and then you have your output. That is, in linear systems, it is the convolution of the two. I forgot the t. X of t convolved x of t. And the reason why the Fourier transform in one designers is also very useful, because I can take the Fourier transform of this Fourier transform. I can take this Fourier transform, and then in the Fourier space, the Fourier transform of y is the multiplication of the Fourier transform of the input times the Fourier transform of the impulse response of the system. And this equation here allows you to understand in log what is happening with your energy. So let's say that I have, let's say that I have an input. This is my x. This is omega. I have an input like this, but h is like this. It's a low pass filter. This is in Fourier again. Now, what will be my output? My output will be this one. Up to here, very good. But then I'm cutting out the high frequencies. So I understand with the properties of my filter, I understand what will be the properties of my output. And that is where all these low pass filters, band pass filters, high pass filters come in. And then, what was the key? That I can transform convolutions into multiplications. So let's start with the convolution. So the next lecture is, okay, let's understand how the convolution is performed with images. And then in the second next lecture, we will see how to do that in Fourier domain. Okay, so let's start with the convolution. So, what is a spatial? Okay, so let's see what is a convolution in one dimension. So you do it. I will do it with discrete signals. I will do it with discrete signals. So we have x of n convolved with h. Okay, so let's see what this is. So you may remember the formula. The formula is this one, minus infinity of x of n h n minus. Okay, so let's see what that means. Okay, so let's say that we have this signal here. This is x of n. If this is x of n, x of m, now my axis has to change the name. But actually the representation is the same. So I have the same representation. This is now x of m. Okay, but now that will be something different. Okay, so let's say that my h is blue. This is h red. Okay, so let's say that my h is this one. It's this. That's 1 minus 1. That's it. And then 0 everywhere. So now I have to compute h of n minus m. You may not remember, but it looks like this. So this is the n axis. Now this will be the m axis. Actually, I will not do it here. I will do it just below this one, so that we can multiply it later more easily. So we have this. This is h of n minus m. And this point here is n. Okay, so let's see how to go from there to there. So there is a minus m. So there is a minus m. So that means that the signal has to be reversed with respect to this axis. Okay, and then there is a shift by n. So it means, so there's a shift by n. It means that it has to be shifted to the right, and this minus m means that it had to be reflected. Okay. Now, if I move my n, if I give larger or smaller values of n, I will be shifting this signal to the left or to the right. Okay, so for every n, for every particular n, so let's say that this one was n equal 2. Let's say that this is for n equal 2. I have to multiply these two signals. That is what the convolution is saying. The convolution says, okay, keep the one x of m as it is. Take the middle of h and shift it to the right position, and then multiply the two. So I have to multiply. I have to multiply these sample. So everything is 0 except these two. So this one goes to here. This one goes to there. So I have to multiply the two. Let's use 3. So this is this auxiliary signal that I will integrate later. sum later. Okay, so I have to multiply, let's put numbers. So let's say this is 1, 1/2, 1/3. So I will have 1/2 minus 1. So this will be minus 1/2. And then 1/3 times 1. So this will be 1/3. And all the rest they are 0. And then you have to add those two. So y then is the sum from minus infinity to infinity of all these numbers. But there are a lot of zeros except 2. So that is minus 1/6. And that is my y, not of n, but my y when n is equal to, because I shift it to n equal to. Okay? And I would do the same for all the n's. It takes a lot of time, but okay, you are very patient, you can do it. The computer can do it very quickly, so we don't care. We only need to understand what it will do. Okay. But then, let's say that my h of n is compactly supported. Okay? I will not be strict now about the labels and all these coefficients, this +1, -1. I will not be careful about it. But let's say that my h of n goes from minus n to plus n. Let's use a different letter. This one. It is whatever, but it goes from minus n to n. And then outside this region it is 0. Then in this region, this point here will be shifted to n. You see, this is the origin shifted to n. And then I'm reflecting. Okay, so that means that I don't have to sum. So I don't have to sum from minus infinity to infinity. It is enough to sum from minus n to n, and then this. Okay? Okay, good. Now, actually, I did it wrong. The sum is not of minus n to n. This is what I didn't want. The sum, it will be shifted to n, so it will be from n minus n to n plus n. Now the limits are correct. So x of n stays fixed. This one is shifted to n, and then I have to add around the region that is defined by this. You see? Okay, so that means that a convolution, what is a convolution? All this applies to any kind of signal, not only to images. So a convolution is, you have a signal, you focus at one point, and a neighborhood of it, and then the neighborhood will be used to produce the output. So the output at that location is coming from the neighborhood of that point. So it is not only the point, but it is the point and the neighborhood. But the convolution is a special operation in the sense that all neighborhoods contribute in the same way. So it doesn't matter where you are, in time, all the neighborhoods contribute in the same way. That is actually, so this is a sum, so that is why it's called a linear operator. It's linear in x and linear in h, in both. And because this h is fixed, it is time invariant. So all these are called LTI systems. And actually, this transformation that we have somewhere, this is true only for LTI systems. Only. If it is not an LTI system, it is not true. So this convolution doesn't tell it is true. So that means, your system, a convolution is you focus at a point, and the output at that point will be a linear mixture with some weights given by h of the neighborhood of that point. And those weights don't change over time or over space. They are all the time the same. Okay, so time to finish. So tomorrow we will continue with the convolution. Tomorrow, next day, Monday.